So good morning, everybody. Today I will try to introduce you to the Julia package Dagger. Dagger is a package that is heavily influenced by Dask. Dask is a Python library. The scheduler, Dagger contains a scheduler, and the scheduler is what is influenced by Dask. It attempts to simplify the workflow when you run code in parallel in Julia. So to give a little example, I will steal a function from Alex that some of you may be familiar with, because some of you may have attended Alex's workshop on parallel Julia before. So in Julia, you can use by default, without installing any package, thanks to the module base threads, multithreading. And one of the functionality of multithreading is task parallelism. It sends some task on available threads. And there is a macro for this in the module base threads. And this macro is at spawn, so threads at spawn. And you can very often, not always, but very often, simply replace this macro from the standard library threads by the equivalent spawn macro from the Dagger library. So if you want to use multiple threads in Julia, the first thing is that you need to start Julia on multiple thread. To do this, either you have to change your environment variable before launching Julia. There's a specific environment variable called, that's actually what I'm going to do. So it's called Julia num threads. So if you change this environment variable to however many threads you want, in my case, I'm changing it to 16, then Julia will automatically spawn 16 threads when you launch it. If you launch Julia from the command line, you can also launch Julia with the flag -t. So that would be Julia -t16. So, and by the way, I am running Julia in Emacs, but I have a script to the left and a running Emacs process to the right. But so this is to the right, the classic Julia REPL. So if I want to use the library Dagger, first I have, of course, to load it with using. Then, because I want to compare it with the multi-threading capability of the standard library threads, I also have to load that module. So Dagger being an external package, I had to install it before I could load it. Threads being in the standard library, you don't have to install anything before you can load it. And then to do some timing, we will also use the external package called benchmark tools. So I am loading this. Now, because I have set my the proper environment variable to 16 before launching Julia, I am running Julia on 16 threads, and this can be verified with the function add threads. So if I run add threads, you can see that I have that Julia is running on 16 threads. By default, Julia will start on a single thread unless you are using some IDE, for instance, Juno, and there might be other which do that. Some IDE will automatically detect available threads on your system and launch a number of threads that make sense based on your hardware. Now, to test some multi-threading speed, I am using an example from Alex, which looks at a very slowly convergent series, the sum of 1 divided by a certain element as you increase that element to infinity will converge if you remove a certain digit from the series. So the first thing that we need to do is to have a function that will allow us to exclude a specific digit. So the function digitsin will tell us whether a certain digit is present in a string, because for this series to converge, we need to remove all the, right, thank you very much. I was about to share it, but that will, thank you, Alex. This is much better. We need to remove all of the numbers that contain the particular digit. So I define the function digitsin, and then I will want to do the sum of 1 divided by some value through a loop if we exclude a certain digits. Maybe Alex, you should explain all this function to give the background, but the background is all in this in the link that Alex shared. And actually, maybe I should open that on the browser. That might just be simpler. Okay, so this series, this harmonic series converges if we remove from the denominator all of the elements that contain a particular digit. And this is why we have this function digitsins that allows to test whether a certain digit is present. And then we can, if this digit is not present, we can run this harmonic series over the cap. N is going to be the cap of our series, the top end of our series. So we want a large value for the series to converge. And digit is going to be whatever digit we choose to exclude. In our example, the digit 9, but that's arbitrary. And this is a good example to assess the speed of Julia, because it forces Julia to run a computation over a large number of loops. So this function here is the sequential function that does that calculates the convergence point of our series without any parallelism. And depending on the hardware, the runtime can be very long. For me, it's about 10 seconds. And the total. So the convergence point of our theory is, well, for the value that I'm using, which is a little slower, I'm using 1 to the power of 8. It is, I don't remember, but we'll see it. So in order to use threads at spawn to run this on multiple threads, we have to break down our loop into a number of chunks and then have those chunks be dispatched on our various available threads. And so this is Alex's function, which is a bit complex, but n is the top of our theory. That's the top of our theory. Digit is the arbitrary digit that we decide to exclude. A and B will be the bounds of a certain chunk, and num subs will be the number of subsections. So we will basically split our elements in 2 groups, send one computation on one thread, keep the other one locally, and then keep doing that. I mean, Alex, it's Alex's function. So if Alex, you want to take over to explain the function, feel free to do that. But if B minus A is larger than n divided by the number of subsections we have. So if we have a large number of elements, we calculate the midpoint, and this is the unsigned greater than sign in Julia. So A plus B positive unsigned value to 1 is actually a way to take is the equivalent of A plus B divided by 2, but moved by 1 bit. So if it always lands on an integer. So if you have an even number here, this is it's simply divided by 2. But if you have an odd number, it allows to still end up on an integer. So that's a little trick to take the midpoint while still always landing on an integer. So we take the midpoint of our values, then we send the first half, so that goes from A, which is our lower bound, to that midpoint onto a certain thread. So thread.addSpawn does exactly that. So from A to our midpoint, that goes to a specific thread. So that's the first half of the computation. The other half of the computation goes from mid plus 1 to B, B being the upper bound, and this gets done on the local thread. Then we want to do the sum of the 2 halves to retrieve the result that was calculated by threads at spawn. We use the function fetch. So if finish was the result from our whatever thread, fetch finish will be the total for that first half, and T2 was the total for the second half. So we sum them up. And when this condition isn't true anymore, when we end up with a much smaller computation needed, then we simply do that locally. So this is simply the series being calculated. Alex, if you want to jump in and say a word, because I feel I've done a very poor job at explaining your function.
Well, it's a recursive function, and in this function, you break it into, so you break the entire loop, the entire interval into two pieces. The left piece is going to be evaluated from the left edge until the middle, and it's going to be spawned on a different thread, right? Yeah. And the second piece is going to be run locally, and then you run this recursively. So the first time you call this function, you pass the left and right edges of your series. So basically the starting and the ending index, so 1 and n, right? And then it starts dividing them into halves, and then each half, so every time the first half is being spawned on a different thread, and then the second half is going to run locally. But then you do this multiple times recursively, and the last parameter in the last argument to this function, number of subintervals, gives you the total number of subintervals that you end up with. So all of these subintervals, except for one, will be spawned with at spawn on some other thread, right? And only one of these will run locally. And so the end result is, if you have, let's say, 16 threads here, and you use n subs equal to, let's say, 16, then you have 16 calculations, and presumably each one is going to run on a different thread. It's not guaranteed that all of them will go to, you know, one sub interval per thread. Most likely what will happen is Julia will dynamically schedule these, and you'll probably have some threads doing several sub intervals. But the more sub intervals you have, the more likely it is that it will have more or less equal load balancing.
Right. Yes, thanks. So let's run this. So we have defined this function, which I called with threads, because it uses the spawn macro from the threads module. So it's a generic function with one method. Now, the function with Dagger is going to be exactly the same function, except that I'm using the spawn macro from Dagger. So here, notice that even though at spawn looks the same, they come from different modules, so they are different macro. So, okay, I have my function with Dagger. So for n, which is the top of our series, I'll use 1 to the power of 8. So that's our n that comes up here. And then I will check what happens if the number of subsection, which wants an integer value, is 1. So that means that this will be run on a single thread, because I'm not gonna cut things in subsections. So everything will be running on the same thread. So if I'm running this and I'm using the btime macro from a benchmark tool, which will exclude, which actually will run a number of rounds of this and will take the smallest value. So it will look like things are taking a really surprising amount of time to run, much longer than the timing that appears, but that's because in the background, the btime macro runs a number of times and then takes the lowest value. And this is particularly important in Julia, because with the just-in-time compilation, Julia takes much longer the first time it runs than in subsequent runs, because you have you need time to compile the first time you run things, unless you pre-compile your functions ahead of time, which you can also do with the pre-compile function. So for this this first run on a single thread, we needed 2.4 seconds, and the sum, so the total, the result is 13.277. Now, if I run on 4, if I use num subs equals 4, so I have 4 different subsections. Oh no. Oh, sorry. Yes, little typo, my bad. I renamed the function to try to make it more visible, more readable, but then I forgot to do it everywhere. Okay, so let me rerun my functions. Okay, so it didn't affect the first run because in the first run, we were not in the condition where we only evaluated the else part of we only evaluated the classic way to calculate the convergence series, because this condition evaluated to false. So that's why the typo was not a problem the first time around. Okay. So now we're running it on with 4 subsections. And we have dropped from 2.4 seconds to 640 milliseconds. And if I did it on 16, but I won't do it to save some time, we would drop even more. Now let's see what happens with the with Dagger function. So on with one subsection, again, this evaluates to false. So this part is run. So basically, I'm running the same thing, except that this time it will take longer because Dagger takes longer to have its scheduler decide where to send elements and then fetch them and clean behind. I will explain that in a minute. So this is actually slower. Okay, now let's see what happens with 4 subsections. And I will also again skip with num subs, like the number of subsections equals to 16, because I, for the sake of time. So btime is great because it is more accurate than the standard library at time macro. But it also takes longer because you have multiple runs that are happening. And the number of runs that happen is something that you can customize. You can pass some arguments to add btime. Okay, so the result is correct. With Dagger function, I get to the same result as the with the with thread function. So that's good. It looks like we're doing the right thing, but the timings just aren't nearly as good. For the our second run with threads, we were dropping to 640 milliseconds, and with Dagger, there's been an improvement, but it's still a lot slower, and that remains true with 16. So let's try to understand a little bit how these differ and what happens. So threads at spawn, again, sends whatever function process follows onto a particular thread. And the function thread ID allows us to output the current thread ID. So for instance, if I type thread ID, it returns 1, and that will always be 1 because the repel always run on thread ID 1. Now, if I use this spawn macro from the threads base library, standard library, this function will be sent onto some random available thread, and the function fetch allows us to get the result. If I only run this thread add spawn thread idea, I don't get any output. I get a task address, but I don't get the output. In order to get the actual result, I need to fetch that result, and then I get it. So thread ID, the function thread ID was run on the thread number 2. Let's rerun it. Okay, now this time it's 3. Let's rerun it. Okay, it's 5. So if I put this in a loop and I print the result, let's say from 1 to 30, I get some random looking values, and I have a total of 16 threads. So it can go in theory from 2 to 16. I shouldn't see 1 because 1 is the current thread idea, and I am sending this function onto some other thread. So I shouldn't see 1 appear, but anything from 2 to 16 seems to be fairly random. Now, so that's the spawn macro of threads. What happens with the spawn macro of Dagger? Let's run the exact same thing. Oh, sorry, I see there are some questions.
No, go ahead.
An
I think
effect of the order of summation of an effect of the. Sorry, I don't understand the.
I think you can continue. So we'll see. Okay. We'll see this on your screen very shortly.
Okay, so okay, with Dagger, I get 3. Let's rerun it. Oh, okay, 3. Let's rerun it. Okay, it seems to be a lot of 3, but let's run our loop to get a little bit more results at once. Okay, I get 3 consistently. So clearly, they're not doing the same thing. Yes, also indeed good observation that the big time macro, in addition to the lowest time, returns the memory, some memory information. And you can see that the memory utilized is, and the number of allocations are greatly superior. So what is going on? And this is where I was hoping that maybe I could use my little blackboard. But a DAG, DAG stands for directed acyclic graph. It's a series of nodes connected by vertices that aren't cyclic. So you can't go back into a circle in it. So Dagger builds some DAGs of computations. So each element of computation can be sent as a thunk, or and now that's the preferred way, an eager thunk. And those eager thunks, once they are run, return some chunk objects that when they are fetched are the result. And in your DAG, each node that is below some other nodes are dependencies of those other nodes. And the Dagger as a scheduler, which attempts to minimize the amount of data transfer by running thunks that need some particular chunks where the chunks are already available. So it tries to do a good job at doing all of that. But as you can see, it's not all that spectacular because it uses a lot more memory than the base spawn, and it takes longer. Now, what is quite interesting is that in this DAG as soon as a particular node, so a particular thunk or the chunk objects that need to be run on it aren't needed anymore. They get cleared unless you tell Dagger to keep them either in the cache or to store them permanently, in which case they were written somewhere. And the location is something that you can choose as well. And so in theory, the advantage of this method is that as soon as some element is not needed anymore, it clears the memory. So in this particular example, why did things perform absolutely horribly? Well, it's because Dagger is really not well suited for loops. As a matter of fact, you can't even pass the dagger.@spawn macro in front of a loop, while you can place it in front of most other operations, because there is no iterative method for this macro. And in the context of a loop, the conceptual idea of a DAG with dependencies and nodes that are connected to each other, and some computations leading to some chunks that are used by other nodes, etc., doesn't really apply. So this is a really poor situation to use Dagger. You want to use Dagger in situations where you will have a series of heavy computations, for instance, heavy computations on some big arrays, and these computations will flow one from the other. Now, another advantage of Dagger is when you run into out of memory issues, because it can run out of core. So if you run out of RAM, Dagger can be very useful there. And since time is going very fast, or I'm going very slow, I should rather say, maybe I won't run the code because things take a little bit of time to run. But rand is a Julia function that allows to create an array of random values. By default, they are float 64. And here I am passing only one argument into rand, so it will create a one-dimensional array, which is also called a vector in Julia. They're synonym. So here I'm trying to create a really, really huge one-dimensional array with 10 to the power of 10 random value. And if I try to run
sorry
this,
to interrupt you, Mary. I want to go back to the previous example. Can you explain
Sure.
why we see in your very last example, we see all threes there? We don't see other thread IDs.
Right. So I don't know why it is 3. It is very consistently 3, but so why 3? I don't know. But the reason why it is consistent is because there is no calculation here. There is no DAG. Like the DAG concept doesn't apply to a loop, because you don't have elements that are connected to each other. So the DAG scheduler doesn't, I mean, I'm anthropomorphizing here, but doesn't see the point of dispatching things to different threads, because it wouldn't speed things up. So the
right. So macro, all these threes, do they come from the same process or from different processes? Unix processes, so in the sense of MPI tasks.
The same process.
It's the same process, just different threads?
No, it's the same thread.
Okay. I thought that Dagger would spawn new processes. Am I wrong? I mean, I know nothing about Dagger. That was just my impression.
No, not here. No, I mean, I can double check. Let me check, but I'm pretty sure. Okay, so let me try to. I have a single Julia process running. No other process got spawned anywhere. And I'm pretty sure that would be the case as, sorry, oops, where am I? As I am rerunning this. I mean, this is so fast that I don't know how to check it live, but I have only one. Well, let's see. How could I, maybe if I split my screen. Okay. Okay, so and if I do this at the same time, I don't know if that would work anyway, but let me run it. Yeah, so I mean, maybe this wouldn't react interactively here, but I think it would. Like I think, or I could run instead htop and search for Julia. Where is my, okay, so I have one Julia process. How do I filter actually? Oh, it's F4. If I filter Julia, okay, so I have a single Julia process, and when I run this, no new process happens. So yeah, so no, it doesn't. So oops. So I have a single Julia process, and Dagger.add spawn here only uses one thread ID 3. Why it's always 3, I don't know, but rebooting my machine, launching Julia many times doesn't change it. It's always 3. So it must be encoded somehow, somewhere. I don't know why. But the reason why it doesn't run on multiple thread makes sense with this idea of DAGs that are a series of nodes connected with vertices, and each node is a certain computation. And if you have a complex computation that has various moving parts, for instance, if you have a large array and you or two large arrays and you square both of them and then you make the sum of them, something as simple as that, for instance, then you would have one node which is the squaring of the first array, another node that is the squaring of the second array, and then the sum. And the way the Dagger, the scheduler cleans the memory behind is that you have your first two arrays. Once the square value is taken, the actual values of the array can get cleared. And then once you have the sum computed, the squared can get cleared. And if you have very complex DAGs, the cleaning behind of the memory of all the elements can save a lot of memory. But in this case, it didn't save any memory because we weren't using a DAG, we were just running a loop. And in the loop, we don't have interconnected elements. So does that make sense, Alex? Or
I guess so.
Yeah, okay. So if I try to run, if I try to create a one-dimensional array of 10 to the power of 10 elements, I get an out of memory error. And that makes sense because there is a module sys in Julia that has all sorts of functions that have to do with system information. And in the module sys, there is the function free memory that gives the amount of free RAM in bytes. So you can transform that into an integer if you want. And just for the little side interesting bit, at least was interesting for me because I don't have a computer science background, because computers are in base 16, you can go from the this value to this value by multiplying the hexadecimal number by it's 16 to the power of the corresponding position. And the letters A is 10, B is 11, C, etc. So D is 13. So, but the int function in Julia can automatically do this conversion. So if I look at the free RAM that I have and I divide it by 10 to the power of 10, which is the number of elements I'm trying to create, I get 2.1 something, and that's clearly not enough because if by default the rand function creates float 64, float 64 take 8 bytes, and so I don't have enough. I need 8 bytes per element, and I only have 2 bytes per element. So this doesn't work. I cannot create such a large array with my system. I don't have enough RAM. So to go around that, there is the mmap module in the standard library, and you can use it in creating a file. Here I'm creating it in temp array. The W plus of the function open makes it writable. And then you can create, thanks to the mmap function of the mmap module, a vector of float 64, because that's what rand will create automatically, and of size 10 to the power of 10. So I'm creating, I'm filling this file that I've called temp array with these, I'm writing a file with this empty array of the proper dimensions, and then I am closing the file. So this saves a file on my system. So instead of using the RAM, I'm going to use a file. And the file size was 75 gig. So it's just monstrous. And then you can fill that X that you have created with rand. And in Julia, when you have an exclamation mark at the end of a function, it transforms the argument in place. So that means that X, which was just a placeholder for values, now gets filled in with random floats. And then I can do whatever I want with this crazy array. I can calculate the sum. But all this works, but it's very slow because you write a file, and also it quickly reaches limitations because for the sum it works. But if now I want to do something a little bit more complex, and that's an example that I took from one of the Julia conference presentations about Dagger quite a few years ago. If you run something more complex, you still hit an out of memory issues because you would have to create so many more of these giant matrices. So this is where Dagger and the way it is able to have all those DAGs connected and clear, not only run things in parallel when possible, but also clear memory that is unnecessary, that's when it comes in handy. You can create a certain, in the rand function, you can pass blocks, which is, it defines well, that's blocks. So it indicates the size of an array operation. So it's it allows you to, so this X node, it creates one node of our DAG. And to get the actual value, you need to compute the result. So I first create a node, so it would be a chunk in that case, I guess. And then or maybe it's a thunk. In that case, I'm not sure. And then I compute it. And then, so this is going to take a long time because it's a huge, huge array, and the Dagger scheduler is not extremely fast. But after I have computed my X in this fashion, I can run this more complex. I can run some sin or cosinus and square them and do the sum, because thanks to those DAGs, once the sin and cos of X are taken, as soon as, so at first you have this X value, so that's one node. Then you have the sin of X on the one side calculated and the cosinus of X on the other side calculated. Once we have those values, we don't need X anymore. So X can be cleared from the memory. Then send, and that's for each element of the matrix, not the little dots. That's, I'm not, I'm doing I am calculated the sin of every single element of my array, and then taking the square root of every single element of that array. The dot notation in Julia is the broadcasting notation. It allows to apply the function to every single element of an array instead of to the entire object. So for every single element of the array, you will have some values in memory that can get cleared as soon as you've taken the sin and the cos, because we don't need them anymore. And then once they get squared, the sin and cos aren't needed anymore, so they can get cleared, etc., until we end up at the sum. And so this process allows me to run, even though it takes a long time, things on my machine while I can't even create, I can't even put the starting array in memory, and even using nmap, which allows to write large elements to file to try to go around that problem, I ran very quickly into limitations. And this is not exactly a very complex computation. It's just a computation done on a very large array. So this is a way that allows Dagger to perform out-of-core computations. And because computing my X node value here is so slow, so long, you can actually save it to file and then load it whenever you need it again. And when you load it, you need to pass in the load function the context function, and the context function will reload how many threads were available, how many workers, how many processes. The context is the is necessary to recreate, to reload the data, because that data was created on a certain context of available threads and processes. So context is yeah, it contains information on your various workers. And so I see we are slowly running out of time. Oh, did I miss something here? I guess so. Yes, indeed. So I'll have to rerun it. I don't think it should change the fact that I couldn't run it using mmap, but yeah, I think this is indeed correct, because I'm only reducing it at the end thanks to sum. Yeah, no, that's correct, because I am doing an element by element of the entire array until I reduce everything with the final sum. So yeah, that is a good point. Thank you, Ben. So because I'm moving through very slowly, when and why would you even be interested in Dagger, since my first example was not very didn't make Dagger shine particularly, but I wanted to use it because that's an example that Alex has been using a lot in showing various aspects of Julia parallel programming, and so I wanted to start there. So Dagger makes sense only when the computation that you want to do could be easily represented in the form of a DAG. So if you can think of, okay, here I'm doing this operation, and then I'm using the result combined with some other element to do this operation, and then this thing gets used for something else. This is a typical situation where Dagger should do reasonably well. The scheduler isn't insanely fast yet, but it's getting better. I've run into various issues. There are things, it's a bit like it's still under development. They started with only things that were created by a delayed function that were only computed when you would run the function collect on them. So you were created all those things that were kind of on standby, and you had to collect them for them to be computed. And now they're moving to an eager execution API, creating eager things with the Dagger at spawn macro instead. The delayed function had a macro as well. It was called @par. But so in the context of a loop, it doesn't make sense. When you have all sorts of moving parts, it might help. If you have, if you need out of core capability, definitely this is something that you should look into. Then you can easily create some checkpoint. Creating checkpoint, you need the module serialization, which is one of the standard library module. And once you load the serialization module, you open a file and you can integrate that into your functions or into your script, into your computation. You can save results to file or to objects or to various things at certain points that you decide, and so that ensures some safety in case something goes wrong during the process. It also has some backup mechanism in case of an out-of-memory error. But for deeper crashes, like if the server goes down, if something else happens, then there's no backup unless you have built them yourself. But they want to implement some form of backup for those other kinds of problems. But an error, like a failure due to out of memory, will be taken care of by Dagger. And all the dependencies below will fail, but you won't lose the result of what has already been computed. It will be automatically saved. So again, whenever you are worried about amount of memory, that's something that you might want to look into. And then it also allows you to visualize and profile your code, except I really never managed to get it to run. So if someone has any experience with Dagger in the audience and got this to run, I would love to hear about that. And it also can run on GPU, but then the Dagger GPU package at the moment conflicts with the dashboard that allows to graph where your computations are being run. So and the Dagger GPU library hasn't been developed in a little bit of time. So it's not a very active part of the project, but it uses the Dagger.jl package, which allows to run Julia on CUDA easily. And if you load the Dagger GPU, then the scheduler can also automatically make use of GPUs if they are available. So it gives you some flexibility that you don't have to encode yourself if the conditions are right. But if you can do the work of, as Alex did in this example, in the first example we saw, for instance, of making parallel Julia work, it's likely to be more efficient than what the Dagger scheduler will do automatically. But in some situations, the Dagger scheduler, with minimal effort, allows a decent result.